Alright, this is the second lecture in our chapter on electric forces. This chapter we're going to get into um, some equations and some constants that are going to be very important. And one constant in particular we will see many times throughout the course of um, physics 2. So we're going to start with what's called Coulomb's law. This is one of the most important laws when it comes to electric forces and electricity to begin just in general. And we're going to first start looking at just two charged particles. And so we have here Q1, well, Q is telling us it's charged, Q1 and Q2. And we have some distance between them. And we use R as distance mainly because it's going to kind of represent a radius in a sense. If you think about it, if you think about one charge moving around that's not supposed to come up. Okay, one charge moving around the other, it's going to if this charge goes around Q1, it's going to create a circle and you have a radius. And there's a lot of times where we have charges moving in a circle and we just get used to using it as radius. Sometimes you may see as just an x because it is just a distance that we're looking at. But it is important to remember this is a distance. And so if we remember based on Newton's third law, so Newton's third law is that when one force exerts or one object exerts a force onto a second object, the second object exerts a force equal and opposite in direction. So in other words, when Q1 is putting a force onto Q2, and it could be a force that is pushing it away, Q2 is going to put a force onto Q1, but it's going to be equal but in opposite directions. So when Q1 is trying to push Q2 away, Q2 is going to try to push Q1 away. So if these are two electrons, for example, electron 1 is going to try to push electron 2 away. Electron 2 is going to try to push electron 1 away. Okay. Now, we also can look at these, and we delete these arrows, as an electron on a proton. So let's say this one's a proton. It's going to put a force pulling Q2 into it. And Q2 is going to put a force on Q1 that's pulling Q1 into it. And so these are, again, equal and opposite in direction. Now, the direction comes from whether or not you are dealing with electrons, or in other words, positive charges or negative charges. And both charges have to be taken into account when we're finding the force. The magnitude of the force deals with the amount of charge for each charge and the distance that they are apart. So if these charges change, if for instance we double the charge, it's going to double the force. If we double either charge, it doubles the force. If we double both charges, then we're multiplying the force by 2 twice. And so by doubling both charges, you actually quadruple the force. The radius works opposite. if you double the radius, meaning they get farther apart, then they actually have less force on them. And it's going to follow the inverse square law. Since in our equation we see that r is actually squared. And so if we double the radius, we actually quadruple, not quadruple, I'm sorry, we divide the force by 4. If we half the radius, then we quadruple the force by 4. And so the radius works opposite as Q1 and Q2. Now, this K is the constant I was talking about. We see it all the time. I actually remember this way more because I use it more than the other constant that's kind of part of it, which is this E sub 0. The K is 9 times 10 to the 9th newtons meter squared over coulomb squared, which I'll get to what coulomb is here in a minute. And the force equation is just that K, 9 times 10 to the 9th, times the charge on the first, the charge on the second, divided by the radius squared, or how close they are squared. That K equals 1 over 4 pi and then epsilon naught. Epsilon naught is what we call the permittivity of free space. We'll actually see one for electrons or electricity, one for magnetism. And this deals with the capability of electron field lines passing through free space. It's also a constant, and this one's harder to remember, but you may get used to seeing it so much that you remember it. And it's 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And so 1 over 4 pi times our epsilon 0 gives us 9 times 10 to the 9th, which is okay. So we can easily write this equation. Let me scroll up so I can write it in. As 1 over 4 pi epsilon naught times Q1 Q2 over R squared. And to be honest, there actually are times that this becomes important to write it this way, because we may be able to get the pi and epsilon naught to actually cancel. And so it's not useless to know that that's what K equals. And I mentioned before, the direction of the force depends on the charge. So if you have a positive and negative charges, they're going to be attracted to one another. And so they are going to try to pull pull the other charge in. And so they will end up actually with a negative force. When you know you have two electric forces, I should say one electric force, is negative, you know that these two charges are opposite one another. When the force is positive, you know these forces are the same, or these charges are the same. And so the proton will repel the other proton, and the electron will repel the other electron. And when that happens, we have a positive charge. Alright, so we also have what's called a point charge. And this idea is just a single charge in space. It may be a electron, maybe a proton, it may be a combination of electrons making up one point charge. and will measure how much charge it has. But it's located at a specific spot in space and not um, separated at all. And then we have the opposite of that would be large objects that have a separation distance harder to tell because the charges can be um, located anywhere on this large object. Right? Point charges we used a lot at the beginning just to illustrate um, the mechanics of looking at electric charges. Now I said I was going to get into the units, and it's important. This is a unit you have not seen, Physics 1, and it's called a coulomb. Now, in our equation, F equals K Q1 and Q2 over R squared, these have to be measured in coulombs. Right? So if it tells you that it's 1 microcoulomb, we have to write it as 1 times 10 to the negative 6 coulombs when we do the multiplication and when we do the figuring out of how much force. Otherwise, if you leave it as microcoulombs, you're going to get a unit that's not going to be newtons. So coulombs times a K divided by a meter squared is going to give you newtons. Now, you don't want micro, you don't want kilo. Micro you'll also see a lot of times nano, which is 1 times 10 to the negative 9 coulombs, and this will be 1 nanocoulomb. Those are the two you see the most often. Those are the type of numbers we deal with. A lot of engineers like to deal with numbers based on threes. That's one of the reasons you'll see it. And even in physics, we usually base it on negative 6 or negative 9. You may see negative 12 and negative 15, or even negative 3, but not so much with charges. The electron is equal to a negative 1.602 times 10 to the negative 19 coulombs. Now this is an electron. A proton, which I'm going to write as just E here, which is basically any positive charge, is 1.6 times 2, oh, I'm sorry, 1.602 times 10 to the negative 19 coulombs. So the proton, the electron, they have the same charge. That's why they can cancel each other out. They're both in coulombs. It becomes a important number to remember throughout this class because you're going to be dealing with this number in many different problems and in many different areas. Now, the negative charges, the protons, so the positive charges, we have what's called charge quantization. That means any object is going to have a charge that is a multiple of this number. Whether it be positive or negative, you'll have a multiple of this number. This is how they actually figured out what the charge is of an electron. And so you may have 3 electrons. 3 times 1.602 times 10 to the negative 19 will give you the charge. If you have 4 electrons, 4 times that will give you that charge on that object. But it has to be a multiple of that number. It has to be a multiple of E or negative E. Otherwise, you're not. It isn't possible. The electron and the positive charge, these are the fundamental basis charge. Think of it as one, in a sense. It's the lowest number that you can have for charges. Alright, so when we're dealing with charges, when we're talking about electrostatic charges, think of this as a charge at rest, meaning there's no acceleration, there's no velocity. We're just looking at the forces between them. So a lot of times the forces are going to cancel each other out, so they're not moving. And then we have what's called superposition, which we kind of have seen before. We may not have mentioned it so much, but all it means is that the net force, and this is the same thing as in physics 1. The net force is force from one object plus force from the second object plus the force from the third object, the fourth object, and so on. All acting on an object gives you the net force. So all the forces add together. So when we have multiple objects or multiple forces from objects, we break them down like we do any other forces. We break them down into x and y components. So if we have two forces here, force 1x will be the force of 1 cosine the angle, and the force 1y would be the force of 1 sine the angle, and the same goes with the second force. Force 2x is the second object in the x direction, that's force 2 cosine angle 2, and force 2y is force 2 sine angle 2. And so to combine forces together, we add them like we do vectors. We add our x's up, so force x, which is overall, force of 1x plus force of 2x. If we're dealing with multiple forces than just two, we'll have force of 3x, force of 4x, all being added in. And each one of these is force of 1 cosine of that angle, force of 2 cosine of that angle. Same thing with the forces in the y direction. Force of y is force of 1 in the y direction plus force of 2 in the y direction, and so on. And so it's force of 1 sine angle 1 plus force of 2 sine angle 2, and so on. And then just like vectors and trigonometry, you have what's called the Pythagorean theorem. And this is the force of x squared plus the force of y squared gives you your overall force squared. Or if you take the square root, then it gives you your overall force. And then the overall angle is going to be that the tangent of the angle equals force of y over force of x, or the angle itself equals inverse tangent, which you should have seen in math class in physics 1, fy over fx, and you will have seen this in the review on the very first day. Now, this isn't anything really new. If you got through physics 1 and you did forces and you did broke it down to components, you're just dealing with a different force now. We're just dealing with the electric force instead. Alright, so we're going to do a couple problems here. So the first one, you have, F1 equals 4 newtons at an angle of 45 degrees. F2 equals 2 newtons at an angle of negative 45 degrees from the positive axis, x-axis. We want to know what the magnitude of the overall force is. So our picture looks like this. We have F1 coming up at 45 degrees. So this will be the 45 degrees. And then we have F2 coming down at negative 45 degrees. And so what we want to do is we want to split these up. Do x's and we'll do y's. So our x for f1, so I'll call it f1x equals 4 cosine 45. Our f2x equals 2 cosine negative 45. And then for y's, f1y equals 4 sine 45. And f2y equals 2 sine negative 45. Alright, so if we put these in a calculator, we do 4 cosine 45, and we get 2.83. So I'm going to do overall x, 2.83 plus the 2 cosine negative 45, which is going to be 1.41. And we think about it, this makes sense. Both of these are kind of in a positive x direction, so they both should add together. And when we add them, we get 4.24. Rounding, of course, here. And then Fy, we'll do the same thing. 4 sine 45, get 2.83. And then 2 sine negative 45, which is going to be a negative 1.41. And this makes sense. One's going up, one is going down. This one's going up, this one's going down. They should not cancel, but they should subtract. So 2.83 minus 1.41 gives me 1.42. Now we want to find where the overall force is and what angle it's at. We know it's going to be in the first quadrant since both our f of x and f of y are positive. So to get f, we do square root 4.24 squared plus 1.42 squared. And once I do that in a calculator, we get 4.47. Yeah, I took the square root. So we get 4.47 newtons. And so this is our force in our coordinate system. So it's 4.47 newtons overall. The angle is again inverse tangent of y over x. So y is 1.42 and x is 4.24. And so this is going to equal 18.52 degrees. And since we know we're in technically the first quadrant, 18.52, We know this is the angle. Nope. I didn't even hit the button that time. Just started drawing. Okay. We know this is the angle coming up off the x-axis. Okay, now that one didn't involve charges. Let's get to one that does involve charges. But it works the same way. We just have to remember what we're looking for. So here we are looking at 3 charges, looking at xy plane. First charge is right there at the origin, charge Q2, 50 microcoulombs. Q3 is above it, and it's 65 microcoulombs. These both are positive. And then Q1 is to the right of Q2, and it is negative 86 microcoulombs. And so what we want to look at is we want to look at the force on Q3. And so the Q3 and Q1 are opposite. So Q1 is going to pull it downwards and down towards it. So it's going to be at an angle. And we see that the angle is listed here as 30 degrees and also listed up here as 30 degrees. That means this angle right here is going to be 60 degrees. As it works with any triangle. We also have the distance that it is away from each other, and that's 60 centimeters. Then we have Q2. Q2 is the same, so it's going to push it away. And we see that we have a arrow on moving away from Q2 on this axis. And so we're going to end up with, we have 2 forces here, so we're going to end up with an overall force that's going to be somewhere in between those 2 forces. These forces right here that you see, this one pulling down and this one pulling to the right, those are the components of the force from Q1. These two we're going to have to find in order to do the math here. Alright, so where we're going to begin, we'll start with the force of 3 onto 1. Okay, and this is going to be K times Q3 and Q1. I'm using small q here. I usually tend to do that. It's no big deal in this case. A lot of times when you're dealing with point charges, you use small q. And then this is going to be the distance from 3 to 1. That's being squared. Right, so for K, it's 9 times 10 to the 9th. Q3, and it actually doesn't matter which one you do first, but Q3 is going to be 65 times 10 to the negative 6. It's a microcoulomb. And Q1 is going to be a negative 86 times 10 to the negative 6. Now, I'm not going to worry about this negative sign. I wrote it in just to show you that I know it's negative. Oh, great, it wants to only play everything. I'm just going to make it positive this way. Gotta love how technology is. Okay. I'm making it positive just because I know what direction this is. I know it's going to be pulling it down. I took that negative into account. Now that I know what direction it is, I won't care about the absolute value of this force. So I'm not going to worry about the fact that this is negative. And then this is over a distance of 60 centimeters. So I got to switch that to meters. Right? You should have gotten used to doing conversions in Physics 1. So I switch it to meters, it's just 0.6. And then we have to square it. So when we put this in a calculator, I get 139.75 newtons. And I wish it wouldn't do that so much. Okay. See if I can delete that. Oh, so it just wants to delete everything. Okay. Try not to do that as much as I can. So this is 139 newtons. And this is from 3 to 1. And this is the overall force from 3 to 1. Next, we're going to do the force from 3 and 2. And so it's still going to be K Q3 times Q2 over R32. Again, that's being squared. Now, this K is still 9 times 10 to the 9th. The Q3 is 65 times 10 to the negative 6. Q1 is 86 times 10 to the negative 6. And we are 30 centimeters away, so it's going to be 0.3 squared. I'm sorry, that is not 86. I got used to doing that. This was 50. This is Q2, not Q1. Putting it in, I realized I'm putting in the exact same thing I did before. Divided by 0.3, divided by 0.3, and I get 325. So this is the force from F3 onto F2 and F3 onto each other. Right, now, these two are the forces being on to Q3. Now we have to put them together to get the force overall. And so this is where we're going to have to break up the forces into components. Now, the components for F32, so F32X and F32Y, are actually not too hard to do because we can actually look and see what they are. They are acting directly in this line, and so the fact that one's pushing up, you're going to have the 325 be completely in the y direction, and in the x direction you're going to have just 0. Now, the more complicated one, it's not that complicated, but the F31X is going to be the 139.75 cosine of the angle. Now, the angle that we have to use here is going to be, since we are looking at 30 degrees coming from the x-axis. That's how we know that we want to use it, because it comes from the x-axis. And so we'll have cosine 30 degrees, which is going to be equal to 121 newtons. And then F31Y, this is equal to 139.75 sine 30. And this is going to be equal to Let me run this through my calculator. 69.75. 0.875 newtons. Right, now what we have to watch out for here is our signs. We know that for the x we only have one component, and that's going to be to the right, so that's going to be positive. So we're okay with that, and so fx total is just 121, and it's going to be in the positive direction. F of y is going to be a little different. They're countering each other. We have 325 up, and we have 69.875 down. So overall, we're going to have a force that's up, and we can see that. But we have to subtract them. So 325 minus 69.875 gives us 255.125. And so what we can do now is we can take and find f. This is the square roots of 121 squared plus 255.125 squared. And we get 282.4. And then the angle is equal to the inverse tangent of our y, which is 255.125, over our x, which is 121. And we should get an angle of 64.6 degrees. Alright, now I am actually going to stop this video, but before I stop it, I just want to let you guys know. These two problems we're looking at, they go from the same diagram as the first problem. They're instead looking at charge 2 and at charge 1. You can try them. You can bring them into me in class to help if you're having trouble trying to work them out. But you can use the example I did to help try to solve these. If I get a chance, I may go through them in a separate video, just those two problems in that video for you to check. I'm hoping that that's going to be something I'll be able to get to. But I don't want to make this video too long, so I'm going to stop here and we'll do the third video, opening up with the electric field. So I'll see you guys in the third video.